Hello and welcome to my Cellular Automata and Procedural Map Generation game development tutorial. In this video, we'll be talking about the Cellular Automata algorithm, what it is, how it works, and how to implement it. Cellular automata are simply methods of rearranging a randomized grid of values into a more organized and aesthetically pleasing grid of values. From a game development perspective, these values are usually tiles on a tile map. For example, in this tutorial, we're going to be using a white tile and a black tile. The white tile indicating a floor, and a black tile indicating a wall. Of course, in practice, we can use more meaningful tiles like trees or cave interiors, but for the sake of simplicity, we'll be sticking to this very basic visual example. There are two images on screen. The image on the left displays a whole bunch of randomized floor and wall tiles. This is what we call a noise grid. It's literally just a bunch of noise on a grid. The image on the right displays a more organized layout of floor and wall tiles. Believe it or not, this more appealing layout actually spawned directly from the noise grid by utilizing a cellular automaton. Cellular automata have been used in countless video game titles, as well as in other areas such as mathematics and biology. The image on the left is a screenshot of a procedurally generated world in a game called Dwarf Fortress. Of course, not all of it was generated using cellular automata, but some of it was. The image in the center shows something called Conway's Game of Life, which is a cellular automata that self-perpetuates and evolves as time progresses. The image on the right is just a bunch of really cool designs that were generated purely through various cellular automata. It's really amazing how something so complex and beautiful can spawn out of such a simple concept. So how do cellular automata work? They're actually way simpler to understand than you might expect. Cellular automata transform tiles based on their neighbors. By neighbors, I mean the neighboring tiles to the tile in consideration. Take a look at the 3x3 grid on screen. Let's do a quick run-through of how the algorithm would transform the center tile, highlighted in green. The first thing we have to do is take a look at the 8 neighboring tiles. We see that there are 4 white tiles and 3 black tiles. And remember, the white tiles indicate a floor, while the black tiles indicate a wall. All we have to do in order to transform the middle tile is follow the conditions on screen. If more than 4 of its neighbors are walls, then the center tile should also be a wall. Otherwise, if 4 or less of its neighbors are walls, then the center tile should be a floor. So in this case, the center tile would transform into a floor since it's surrounded by only 3 walls. Now let's take a look at the tile on the top right corner of the grid. In order to decide what it should transform into, we need to look at all 8 of its neighbors. Since this tile only actually has 3 neighbors, since it's on the border of the grid, we'll go ahead and consider the positions outside of the grid to also be wall tiles. Keeping this in mind, we can count that there are 7 neighboring walls and only 1 neighboring floor. Therefore, this tile should become a wall. Let's do one more. The bottom center tile is a floor once again. Checking its neighbors, we see that there are 5 walls and 3 floors. Therefore, this tile should also become a wall. Note that we don't have to use this exact rule of greater than 4 or less than or equal to 4, but this is a very common rule to use in game development and has proven to provide some really nice results. Also note that the terminology for considering all 8 immediately surrounding neighbors is called a Moore neighborhood. Now we're going to quickly run through another example, but this time we're going to proceed exactly as a computer would. We have a grid on the left side of the screen. This will be our tile map. It consists of a 3x3 area of floors. We're going to start at the top left and work our way rightward and downward. Recall that if a tile has more than 4 neighbors that are walls, it also becomes a wall. Let's get started. Looking at the top left tile first, how many of its neighbors are walls? Well, there are 5 positions to consider outside of the grid, so we have to tack those onto the wall count. The others are all floors. Therefore, since more than 4 of its neighboring tiles are walls, this tile should also become a wall. Before we look at the top center tile, notice how I didn't overwrite the original grid with that new wall tile. Instead, I placed it on the right side of the screen in what will become a new grid. This is crucially important. When we implement this algorithm, we need to remember to save our results in a grid separate from the one we're using for our floor and wall comparisons. If we don't, the algorithm will quickly break down and pretty much consider every single tile to be either a wall or a floor. Okay, now let's continue on to the top center tile. It has 3 neighboring walls and 5 neighboring floors. Therefore, it becomes a floor. The top right tile has 5 neighboring walls and 3 neighboring floors. Therefore, it should become a wall. When we hit the edge of the map, we simply go down to the next row and continue until all tiles have been covered. And that's it. We just completed an entire iteration of the automaton. Like I said, it's a surprisingly simple idea that can show some really awesome results. Of course, a 3x3 map isn't going to do much, so let's get a little bigger. We're going to jump into the actual implementation now, but before we do, I want to go over a few things. All the code shown on screen will be pseudocode. This is to ensure that I'm not being biased towards any particular programming language. Everything done here can be achieved in every language, it's just a matter of understanding the concept and translating the code. My personal example will be built in the default game engine because that's what I'm most familiar with. Additionally, after we cover the implementation, I'll show off an interactive HTML5 demo that you can navigate to and play around with. This demo will allow you to manipulate various properties of the cellular automaton discussed in this video to gain a better intuition for how it works. All of my source code can be found on GitHub totally for free if you're interested in seeing exactly how I wrote the program. The first step to implementing the algorithm is generating a noise grid. Remember that the noise grid is simply a randomized set of values which matches the desired size of your final map. The important thing to know here is that we need to set a particular noise density when creating the grid. The noise density refers to how much of the grid will start as walls instead of floors. It's most intuitive if your density value is between 1 and 100, so that we can interpret it as a percentage. For example, the top image shows a noise grid of density 50. Approximately half of its cells are walls and half of its cells are floors. The middle image shows a noise grid of density 10. Approximately 10% of its cells are walls and 90% are floors. Similarly, the bottom image shows approximately 90% walls and 10% floors. Realistically, you never want a density value this extreme in either direction. From experience, procedurally generated maps look best between maybe some density value of 45 to 65. Again, you'll be able to get a better intuition for this stuff by playing with the demo. Now let's actually generate a noise grid in code. Line 1 defines the makeNoiseGrid function, which takes a density value between 1 and 100. Line 2 initializes a two-dimensional array that matches the width and height of our desired map. This is the array that will hold all of the grid values. Line 3 generates a random value between 1 and 100. Now we're going to loop through our noise grid array and begin initializing its values. Line 5 checks if our randomly generated value is greater than our density argument. If it is, then the current tile in the noise grid becomes a floor. Otherwise, it becomes a wall. Once the whole grid is populated with floors and walls, we return the noise grid so we can use it later. Now we can move on to the second step in the implementation, which is the cellular automaton itself. The animation on screen shows a noise grid being fed through a cellular automaton. If you look at the bottom of the GIF, you'll see that the noise density for this map was set to 60, meaning it started with approximately 60% of its cells as walls. You'll also notice that there's a variable called iterations. This refers to how many times we want to feed the noise grid through our cellular automaton algorithm. When we perform cellular automata, we don't just do it once, we do it multiple times. Remember that exercise where we scan the 3x3 grid from left to right and top to bottom? That's considered to be one iteration. When we have a really big map like the one shown on screen, we need to run that same scanning procedure multiple times in order to achieve an appealing result. You'll notice that as the iterations increase, the generated map begins to look smoother and smoother. The amount of rigidness slowly starts to fade as we increase the iterations. This is an important intuition to have. If you're looking for a map that contains a lot of small corridors and obstacles, then maintaining a low iteration value is probably what you want to do. Otherwise, if you're looking for a map that's more open and expansive, then consider maintaining a high iteration value. Here's the routine in its entirety. We start by defining a function that takes two arguments, those being the noise grid that we generated from the noise grid function, and the number of iterations we want to do, labeled here as count. The for loop on line 2 serves to repeat the algorithm for the specified number of iterations. We start each iteration by copying our grid into a temporary grid. The temporary grid will be used for scanning the map from top to bottom and left to right, and counting the neighboring walls. The actual changes to the grid will be applied to the original grid array. Line 4 and 5 begin looping through our tile map, from left to right and top to bottom. On line 6, we initialize a variable called neighbor wall count. This is a counter variable that keeps track of exactly how many of the current cell's neighbors are walls, just like we did in the examples. The following two for loops check the current cell's neighbors, from left to right and top to bottom. If the current neighbor is not within the tile map bounds, then we consider it a wall and we increment the wall count. Otherwise, if the current neighbor is within the tile map bounds, then we continue on to line 10. Here, we check if the current neighbor is equal to the current cell. We have to include this check because we don't want to mistakenly consider the current cell as one of its own neighbors. That would be wrong, and it would lead to a situation where we have potentially 9 neighbors instead of 8. Finally, we check if the current neighbor is a wall tile. If it is, we increment the wall count. Those inner for loops will continue until all of the current cell's neighbors have been checked and tallied. Once this process is complete, we move down to line 15. Here, we check if the finalized wall count is greater than 4. If it is, then the current cell should be a wall. If not, then the current cell should be a floor. And that's it. This procedure of scanning each cell and its neighbors will continue until we reach the bottom right portion of the map for the specified number of iterations. Now let's put it all together. Thinking on a more macroscopic level, there are 3 components to getting a procedurally generated map up and running. First, we create a noise grid with some density value. Second, we apply our cellular automata to the noise grid for a number of iterations. Finally, we draw the tile map onto the screen and observe the results. Okay, so here's an example of that interactive demo I was talking about. You'll be able to find the link to this in the description of the video. And the first thing I want to show off is the strip of instructions at the bottom. You'll see that there's a noise density, there's an iteration count, then there's the controls, and then Gymrat Games, which is my studio name. So let's start with the controls. You can press 1, which will increase the noise density. So here we can see that we have, it's set to iteration 0, so it's not actually running the cellular automata algorithm. Instead, it's just doing the noise grid and then displaying it onto the screen. And if we increase the noise density, say to 70, you can see that the walls are becoming more apparent than the floors. And if we decrease the noise density, let's go down to say 30, then you'll see that the floors start to overtake the walls. The parameters that you use for the noise density and the iterations are going to change depending on the size of your map. So if you have a really big map like this one, you're going to want more noise density and more iterations. But if you have a smaller map, you're going to probably want maybe around 50 for your noise density, and then maybe around 3 or 4 for your iterations. So let's go on to the other controls. 3 and 4 are grouped together. The 3 will increase the iterations by 1 every time you click it. So you can see that we're applying Cellular Automata, our algorithm that we implemented in the video. Every time we increase the iterations, it generates a new map and it runs the new noise grid through, say, 5 iterations of Cellular Automata. And now it's 6 iterations, now it's 7 iterations. And you can see as we increase the iterations, the smoothness, what I like to call the smoothness of the map increases. So if we go up to, say, 15, all of a sudden everything's really smoothed out. So if we press 4, we can decrease the iterations. So here we have very long, narrow corridors. Note that every time you increase the iterations, the algorithm does run a tiny bit slower because it has to scan the map more times. Let's go up to 10. And then if you hit the 5 button, it'll actually just regenerate a noise grid and a new map with the current settings. So the settings won't change. And you can just generate maps that all look kind of similar to see if you like this setting and you want to use it for your own game. And if you hit the button 6 on your keyboard, it will actually step up to the next iteration without generating a new map. Let's just go with 2, the same exact map without generating a new one. We can click 6, and it will do one more step of Cellular Automata. One more step, one more step, one more step. So you can kind of see how the map evolves as the noise grid is fed to the algorithm. And like I mentioned, or I will be mentioning, All of the source code will be on GitHub. In order to open the source code in a proper editor, you have to be using the default game engine. That's what I wrote this in. But you can also just open up, there's a folder called example, and then there's a script called main.script. And if you open that up, you'll be able to see all of the primary code, like the actual implementation of the algorithm.